Record. Yes, this is Grace Hopper, Grace Murray Hopper, Admiral Hopper, Dr. Hopper, lots of titles. But kind of just stumbled around this quote. One, this is my efforts to make Hopper a household name, so we get to see her twice. So there'll be a few folks that we get repeats of, but I just thought these were interesting anecdotes from one of her, I think this is from one of her Turing Award-winning speeches, but she said, "Humans are allergic to change. They love to say, 'We've always done it this way.'" And she said, "I try to fight that. That's why I have a clock on my wall that runs counterclockwise." So I thought that was just kind of a cool sort of mentality thing to, motivate yourself. And, that was hers. And then she also said, "Life was simple before World War II. After that, we had systems." Oh, that's a dig at the systems person, I guess. But anyway, just some words of wisdom, lots of great incidents like that. I haven't personally read any biographies, but that is something that should be on my reading list. So maybe some of you folks have, and I'd love to get those recommendations of good ones for her contributions to science and many other things. Okay, so with that said, let's go ahead and start with our Scrum. As I was mentioning, it feels like I haven't seen everybody for such a long time. So our weekly, or what feels like monthly Scrum here. What we were working on last class was debugging. So hopefully getting some skills, work with our interactive debuggers. And again, as whether I'm giving you code in the labs or for the assignments or these kind of things, the debugger can be a great tool for just, running that support code and sort of stepping through it and seeing how it's working, what functions are executing. So we do want to get in the habit of using some of these tools. It's our sort of get out of trouble tool, when we can use GDB, LLDB, or whatever debugger that you choose to use. So we learned about some of the different things you can do: breakpoints, stepping through your code, getting call stacks, BT, and some of the more advanced things like attaching to processes, or looking at virtual table, or some of these other things. And in order to make use of our debugger, the thing that we're always going to remember is just to compile our code with -G, as well as with the warnings too, just to give ourselves some extra protection from the compiler to say, hey, maybe something could be going on wrong here. Okay. And then we learned about some other things, looked at printf debugging, macros, and so on. So that's what we were working on last time. Any questions or comments about debugging, lab stuff, homework stuff? What's going on? Yeah.
So I thought it was really interesting on the lab exercise when we did the out of bounds on the array.
Yeah.
It took like 1,000 elements for it to segfault.
Yeah.
Is that because of that's like the page size or something?
Yeah. Do you remember what the exact number was?
1,240.
1,000. What about for other folks?
I think mine was like 1148 or something.
48.
Mine was 511.
511. Yeah.
Mine was like 1170 something.
119.
I think it was an 8 at the end.
An 8. Okay. So quite a range here, for the segfault. So one that was a little bit alarming in the sense that you can go out of bounds. So and we don't get an error there. One of the reasons why is because when we have a process, here's our process. I forget what it was called, /prog or whatever. And we always get a little bit of stack space by default, and usually that's given to us in page size increments. So page is usually 4,096 bytes. So depending on whatever that number is divided by 4, it's probably in this range of 1,000. There could have been other stuff allocated there, or sometimes this default size might be something else, depending on if you were Windows, Mac, or Linux folks. That was something to show, I guess, that our debuggers, we really do need them. We can't always rely on our program to crash, in a sense. And this is why we're going to also sort of defensively program and lead us into our topic today, which is testing. So before we access an array, maybe we do that through a function that says, are you sure? Is it less than the size? Because otherwise we get this weird behavior. So really simple program, but the results. We have to think about our systems knowledge, and we can't trust our language. I think it was bounded to 10 or something, right? It's int array 10, or one of these options. And as you can see, it changes based on what system you're on. Yeah. So that was kind of a fun one. Sometimes they call that the red zone too. It's sort of no man's land would be the sort of slang for it, but it's like, okay, you really just have 10 elements, but whatever can go on in this space here. Other questions, comments, thoughts about anything we've been working on the last week? Lab stuff, debugging stuff, homework stuff. I have had some requests from one of the TAs to do a video on homework stuff, so I'll probably do that tonight at some point, just to help with folks who are working on that. Just a command pattern example, just to help with that. Anything else? All right, logistics-wise, so what we're working on today and sort of what's going on in the class. So of course your Lab 5 will be due shortly. Lab 6 will be out today, so we'll talk about that towards the end to practice some of the things we're going to talk about today with regard to testing. A3 is due the 20th, so you have a little bit more time for that. And then we have an exam coming up next week. So let's just take a quick look at that on the calendar. So we go here, teaching. All right, so here we are. And the exam is on Canvas. That means it's online. That means we don't have to meet in person. I won't be here. You're welcome. You're welcome to be here if you're the only person in the classroom, I guess. I should say, but it'll be an online exam. There is a study guide here, just on topics, ideas of things that you should know about. So we're going to talk about testing stuff today. That would be fair game. Version control stuff, CMake, maybe some of the object-oriented concepts, and maybe just a little bit about the patterns. So anything that's been on labs, lectures, assignments, and so on is fair game. I tend to make the exams pretty, fair. They're a small portion of your grade, 10%. And I just want to know how you think. So usually that's means multiple choice for some portion and then short answers. I want to sort of know about trade-offs. If you can defend your answer reasonably well, that's usually fine. And that's what I care about in this class, understanding the trade-offs. So a recommended way to study would be to go through this list, try to think about what some of the important concepts were, maybe look at our table of contents here on our website, and sort of go through some of the topics and say, okay, shallow and deep copy. What was that? Why was it important? Why would we need it? These sort of things. So logistically, that might be how to study. You might look at something like the singleton pattern and want to understand pros and cons. Okay, so understand sort of both sides of anything. I'm trying to think, adapter pattern, all the patterns that we've talked about. I'm not going to throw any random new ones that we haven't practiced, but ones that we've looked at. Let's see. Otherwise, just logistics on the exam. Again, it's going to be online, multiple choice and short answer questions, some mix of that. The exam is, open book and open notes. So you can, take a copy of that cheat sheet and fill in everything, that you know about those topics. That's actually a good way to study. It's actually a nice deliverable to have after the class too. The cheat sheet that you build so you can remember this class forever. But the catch is with the test, once you open it, you'll have about 3 hours or so to complete it. So you do have to complete it in one sitting. And you can't collaborate with any other students. You can't post to Piazza, can't post to Stack Overflow, those kind of things. Yep.
It's available all week, right? Or like.
Yeah. So
It's
basically,
not like all like one
Right, yeah. So anytime between the 25th and the 30th where you have, 3 hours or so to sit down and take it, you're good to go. So for you folks, ideally that could be, 1 week from now or whatever. Just sit down during this class time and take the exam. Questions or comments? Yeah.
So we're not using one of the lockdown browsers then?
No, just whenever it's on Canvas. Yeah. The lockdown browsers, I think, have a lot of spyware and stuff on them, so I don't like those.
Yeah, and they're a pain in the butt.
Yeah.
They don't work after that.
Yeah. There's some where you have to have, like,
Computer.
oh, what was that?
You can just bring a second computer with you to the exam.
Oh, yeah. Yeah, there's all sorts of ways to get around it, right?
Yeah.
I have 5 computers at home, so, I can be, like, all over the place. But yeah, you can use books, whatever you want, that's fine. Because it's not really going to matter, because I just want to know how you think, right? I think that's how a software engineer works. You have a bunch of information in front of you, and you got to put it together into something that makes sense.
But we can access like online resources during the exam, right?
Yeah, you could look at my website. You could look at the slides if you want. That's totally fine. Strategically, you just got to manage your 3 hours. Yeah.
And is it going to take like the entire 3 hours, or is it just like a added before?
Yeah, so it'll be designed to take like an hour and a half or so. You should have plenty of time. Like I said, most of the time exams are a good way to study, sit down, and think about all the stuff that we've learned about. I'm not going to try to do anything tricky, right? I'm not going to throw a 1,000-line C++ thing and say understand this or whatever. Maybe a pattern, or I might ask you how you would build something, what pattern might be appropriate and why, those kind of things. I think for folks who took 5008 with me, maybe you have an advantage. It'll be this similar style. For everybody else, short answer, multiple choice about trade-offs. So.
So the kind of questions like where you will ask like about our perspective, so those can be like very subjective answers, right? So how are you gonna like grade those? There could be like multiple right answers.
Yeah, so I grade all of them, and that's how it'll be done. Let me try to think. So if I gave you a design pattern singleton and said, is this the right pattern? As long as you can prove yes or no. And demonstrate you know enough about it, that's fine.
Okay.
It won't be a binary sort of thing. Yeah. Other questions? Tessie? Yeah, Mara.
When do you get grades for all assignments and labs?
I think A2, so assignment 2 should have rolled in for at least some set of folks today. Labs, I think through 2 and maybe 3 is coming in today. And then hopefully more. The game plan was to get sort of up to date and caught up. In that next week, I think we'll have pretty much everything graded by the time we get through the exam week. The in-class stuff I've got to enter, but if you've been entering those in as you've gone, you should be in good shape. Other questions, comments about course logistics stuff?
When are we gonna know about like our project partner?
During the exam week, I'm going to send out a survey asking folks about various things, what operating system you use, when you're around, when you're available, in general, those kind of things. So then we'll 2 weeks from now, basically, you'll have a team. Yeah. And that way, you'll have some team members. To bounce ideas around for the assignment, and then basically everything else in the course is group work. And we'll talk about how to work in groups efficiently and some of those things as well. Other thoughts, logistics, where we're at? Yeah, by next week we're halfway done with the semester, so it's like that happened fast. But we're learning a lot. Hopefully we're learning a lot. All right. Well, with that said, let's go ahead and get into testing today. Well, before we do that, Anything blocking, folks? Yeah, I know homework 3 has been a difficult one in a way, but I'll add a video to maybe mitigate or help that. Some folks have gotten through it. Alright, some are still working. Yeah.
I'm still finding it difficult to like where to put an asterisk and where to put an ampersand like reference and
For
yeah.
like pass by reference
Yeah.
and these kind of things. Like when to make that decision, or
I mean like when like it should actually return a pointer like a string thing or like an address. So usually when you're actually writing the function of that sort, especially in the singleton class, right? So if I'm like writing it in a new way, so it kind of get stuck there.
yeah.
If you can like recommend some resources.
Let me open up the repository and just take a look at. Let's see where we had. I think our first singleton pattern here. If it shows up, yeah, I guess here's an example where we have something with an asterisk or ampersand with it. Actually, let's make this really big so folks can see. So when we have the ampersand here, that's when we're returning something that already exists. So in our singleton, so in our constructor here, that's private here, that's normally where we'd be constructing, our singleton here. Or we might be actually doing that in get instance, right? In this particular lab, we're sort of doing, hey, if your instance of your singleton doesn't exist, you allocate it in this function, and otherwise you just return a reference to it. So actually, let me kind of do a little code for this one. Oops, let me leave this up here. Just to maybe clarify this. Let's see, singleton. Oops, I guess I have it already. Singleton 2. Alright, so actually, we don't need any of this stuff. Class. Okay, that's as big as it gets here. Our singleton. And we've got some private here. Public. And really what we care about here is this sort of get instance function here. And I think the question is, do we do singleton with a asterisk here, so return as a pointer, or a reference here? Okay. Now typically, so what this is going to look like is we're going to have also some, instance in here, singleton, my instance, something like that. Usually this is a pointer because we have to allocate it. And then we did this, well, I guess we could do this a couple ways. We were doing this with static here, right? Something like this. Static my instance equals new singleton. Okay, just like that. So this guaranteed that it only allocated one time. Now we could just return our singleton as a pointer, like this. We prefer to usually do it by reference for performance. So usually when you're seeing by reference, we would just return the actual value behind it, right? So we dereference this singleton like this. Okay. The reason we just return the dereferenced one is usually we don't like returning the actual pointer, because if I return the actual pointer, then somebody else can write delete and then whatever this singleton is. So here's like the actual value here. Okay. Let's see. So this is correct here. This is our return value here. Okay. And then this is a singleton, right? So we got to do some other stuff and say, this is static and so on.
So if we were to return it as a pointer, right? So you actually remove the ampersand, but you didn't put the asterisk there. So it shouldn't be singleton asterisk.
Singleton.
If we remove the ampersand.
If I remove this?
Yeah, then if we want to return it as a pointer, so shouldn't there be an asterisk over there?
Yeah, if I want to return it as a pointer, I would just put an asterisk here, and I get rid of this because this type here is a pointer.
And this is also fine just for like the safety purposes. We do not want to.
For safety, yep, yeah. Yep, so we tend to like to return values, and again, so I'm not really giving the user a choice, right? I have this function here, I only have one way to get an instance, the actual singleton, and it avoids me, so let me just write it in comments, by returning the reference or alias to the actual object or value, the user cannot just delete the pointer, right? Because pointer is pointing to addresses, and if we're pointing to memory, then we could call delete on it. Yeah. So if you implement a singleton and you return a pointer, you'll probably see examples like that. That's still a singleton pattern. But that could be one of the things where you sort of say, well, singleton's kind of dangerous because it leaves rooms for these mistakes. Maybe it's hard to implement. So these would be some good trade-offs to think about as well. Yeah. So it's that's also sort of the good and the bad about C++. It lets you do a lot of things in different ways. So you have that control, and you have to think about it, which is good. But that's also sort of the bad thing. You have to think about it. It works sort of both ways, right? There's room for mistakes, but it gives you the power to really think about how you want to implement something.
Maybe we have testing strategy to test this as well. If we have vulnerabilities and things.
Yeah, this will be good. Maybe I'll leave this one up in the background when we talk about testing. Maybe we can circle back and think about how would we test this and try to avoid creating problems. Because for instance, right, as I did, we don't have to have the singleton here. We could have made it a private member variable and returned that as a static thing as well. So there's a lot of these little design things. But yeah, let's think about that at the end. Other questions or things that I can clear up, either a C++ question that's going to move you far ahead or whatever. If not, we should have time at the end of class too for a little bit of one-on-one or whatever. Alrighty. Let's hop into the slides here. We're unblocked on singletons now. All right, so we'll talk a little bit about testing today. So we've learned a little bit about debugging, how to find the bugs. But a natural next step to do is say, okay, we found the bug, but how can we test for the presence of that bug to see if it exists, or just for the lifetime of our project, make sure that bug never reemerges. So that's really what today is about, the testing portion. Okay, so we've spent 5 weeks. Like I said, I can't believe it's already been 5 weeks, but kind of learning about constructing software, whether that's been just learning C++ things, object-oriented stuff, various design patterns, debugging's sort of part of that. But now we want to, go into a different phase, and this could be, a totally different role as a software engineer where you're just testing things. Okay, so let's get a little bit of wisdom. We'll start off with some wisdom early here. This is from Dijkstra, somebody that you're going to see many times in your computer science career. And he has this quote. He says, "We must not forget that it's not our business to make programs. It's our business to design classes of computations that will display a desired behavior." I say, okay, that sort of makes sense, right? We're not just writing software, but it should be doing something that we desire, right? It should be working to our specification. So that's actually the first part of maybe the more famous quote that you've heard, in which he says, "Program testing can be a very effective way to show the presence of bugs, but is hopelessly inadequate for showing their absence." Okay, so that's actually the famous part. That's probably the famous part. I've quoted, I know, in 5008, as well as other classes, actually. But that's the sort of, idea behind testing. We can write as many tests as we want, but testing sort of exhaustively, improving our program will never have bugs. That's a lot harder. Okay, almost impossible for a lot of programs. Okay, but I do actually like this other part because this gets sort of lost in the context when you see some of these famous quotes, sometimes it's worth going back. In Dijkstra's case, you can actually read some of the manuscripts from where these come from. Same with the Hopper quotes that I gave earlier. So I do like this part here, that it's our business to design classes of computation that will display a desired behavior. Okay, we want programs that do what they say they're going to do, or at least what our intent is. All right. So we sort of agreed from last time, or at least I put out there that these bugs that we had previously were bad, and how could they have been avoided? Likely, some of these were probably, issues of bureaucracy where maybe they were spotted by the engineer, but it just didn't get to the right person to, fix this actual problem. So how could those bugs have been avoided? Where is the right place to get them in? And oftentimes it is in the software, in the testing phase. Okay, so I want to talk about software verification and validation. And again, these are going to be our two tools separately, software verification and software validation, to at least increase our confidence that our software is achieving its desired behavior, whatever that might be. There is a little Venn diagram here trying to separate what some of the different tools are, verification and validation, and then in the middle you see here testing and some different types of tests. Things that you might have heard of, unit tests and some of these things. They could actually belong probably in both, some of these items here. So there's a little bit of overlap, but I at least want to distinguish a little bit what I mean by verification and validation. Okay, usually these terms are used interchangeable, but let's try to nail them down here. So the two general techniques, and there's actually a third one too, that often gets omitted, but so software verification, the process of evaluating a system or component to determine whether the product of a given development phase satisfy the conditions imposed at the start of the phase. Okay, so this means writing some test or a test suite, pass a bunch of tests, and we say, okay, it's good to go. Run the rest of the program at this point, right? We verified it works. Okay, so we have some sort of confidence. If it passes 100 out of 100 tests, we're good to go. Software validation is the process of evaluating a system or component during or at the end of the development process to determine whether it satisfies specified requirements. Okay, so on the other hand, we're running our program, maybe it's our paint program, and does it paint the right picture? Does it paint the Mona Lisa at the end? If it doesn't, it's not a good program. Okay, so that sort of was our model of what we thought was going to happen valid. Okay, and then there's this third one called certification. We're not going to really worry about too much, but this is just some written guarantee that a system or component complies with its specified requirements as an acceptable for operational use. Okay, so where you'll see certification sometimes is maybe security. This is very common. The C programming language is sort of famous for this. There's a C cert guide, they call it, that says, hey, your program won't do this, this, and this. You get it certified if it passes these 140 or so different tests, and then you get a check mark next to your software, essentially. Okay, and then they say, yes, this C software is safe, and usually this would be for safety critical systems, your Teslas, your NASA, these kind of applications, things in cybersecurity especially. All right, so let's look at this first one, software verification. Again, evaluating our software at the start, and some of our different verification techniques. Okay, and some of these you might have seen before with different names. But three types of verification techniques. The first being functional testing. Okay, so identifying and testing all the functions of a system based on some requirement. And this is also known as black box testing. And just saying, hey, I've got some function, I'm going to execute it, given some input, and does it meet my output? I don't care how it works. That's where the name black box comes from. I can't see inside the box or what the components are or how it's doing its magic. But that's, all I care is that the given output matches what I would expect. On the other hand, structural testing is identifying all of our functions again of a system, defining the requirements, and given the implementation. Okay, so the difference here with white box testing is I can actually see how it's working. I have the source code right in front of me. And I'm going to write my tests based off of, my sort of domain knowledge. Maybe I'm the programmer who actually wrote the algorithm. Okay, I can see all the edge cases. All right, so that's functional testing. We just care about how it works. Does the input give us, does functional, if you give an input, give us the expected output? Structural, the same idea, but I can look inside and sort of test more explicitly for edge cases. And then we have this third type of verification technique called static testing. And it doesn't really involve the operation of the system or running code, but it could be things like stylistic checking. Are all our variables named with uppercase letters in sort of that fashion? Are variables, named appropriately? Things like const correctness, we haven't talked about it as much, but it could be things like, did you define a copy constructor, a constructor, and a destructor every time you created a class? That'd be sort of part of this consistency checking. Okay. And then we also have measurement techniques. So we might want to be able to measure how good software is. So this is a research area I've worked on, that your input is your source code, and you just want to know how good is it, how safe is it, could it crash, and maybe you get a score, A, B, C, or whatever, just some sort of metric. Sometimes these get critiqued. I'm going to show you one, and you can tell me if you think it's good or valid, but we'll look at one of these measurement techniques. All right, so looking at these just a little bit more in depth. Again, functional testing or black box testing. And again, you can sort of just remember this as given a function. That's where the name functional testing comes from. We're going to write some tests based off of some specifications, or user stories or requirements, whatever our specs are that we wrote in the previous labs here. That's going to sort of guide us. Okay. Does a specific input give us a specific output? And again, the person writing these tests doesn't know how a function works. So if I have this function here, is palindrome, and I know it just returns true or false, well, I should be able to look at the input here, DAD, D-A-D, and that is in fact a palindrome. So it should return true. Okay, so I could write a test here to verify that. I don't care how it works. I don't care if it uses a O of n cubed algorithm. That'd be a little bit wild here, but I don't care. But it should just return true. And then the other case, ABC, that should return false. Well, it's going to return a Boolean value, so I should have one for true, one for false. If it passes that, the two possible test cases, I'm probably okay. Okay. What other edge case might you want to test here? I've got one for true, one for false.
Empty string.
Empty string, yeah. Another edge case. Maybe
Single letter.
null string, single letter. Numbers, yeah, so if I just put in either just purely numbers or strings and sort of see what happens. Yeah. What was that? Symbols as well. Yeah, special symbols. See if it breaks. Maybe Unicode, like smiley faces and these kind of things. Right? So we can get pretty exhaustive with some of these tests, and that's probably a good thing to do for these. Okay? So the more tests we write, the more we increase our confidence. It doesn't cost us too much. All right, so the opposite of that, or a different type of testing, I should say, not opposite, structural testing. So again, structure, I can see inside how the actual code is implemented. So we often call this white box testing. Or you might hear the more modern, like clear box testing. I can actually see through the box and see what's going on here. And this one, we're writing tests based off of the specification. Okay, and the source code. Okay, so I'm going to show you a snippet, give everybody, 30 seconds or so to see if they can, tell me if there's an error, if it's a good test or not. But here's an example of what you do with white box testing. So I have is Palindrome here. I've got a test here. And, this is a white box test because I can see what's going on. All right, so does anybody want to point out the error or what's going on in this code, or why we might want to, have knowledge of the code to figure out how to write our tests? Maybe it's pretty obvious here. Right, Trevor implemented this. Maybe they looked at the code and they said, okay, Dad, maybe see those are only strings being used in the programs. I'm just going to handle those special cases. It's Friday, it's 5, I'm going to leave. Or whatever.
They looked at the 2 tests, developed towards the test, and called it a day.
Yeah, I mean, technically they're good to go, right? 2 out of 2 tests passed, and then the boss is happy. Yeah, I mean, I've seen this in my undergrad where this is a poor, panicked, person was working on a homework and they just figured out what the string was, the program was going to output, and they just kind of did a printf, whatever that string was, and you got to salvage some points, right? So you can do that. But so obviously this is flawed here, right? And by seeing inside the code, we can say, well, okay. This algorithm is clearly broken as soon as we add a 3rd or a 4th test, right? We might even get lucky sometimes where it's just returning true sort of randomly here in the default case, okay? All right, so when we're writing our code, we're going to sort of be guided by looking at what are the potential return values. So for a Boolean, again, true or false. Maybe if we have an int return type, we have a range or something. But then what are the different branches that we can take here? Maybe trying to exercise those branches, and then trying some of our edge cases, right? So all the ones that you folks mentioned, the empty string, symbols, more letters, numbers, etc. are going to break that. All right, so the other technique here is on, we call static testing, okay? So this would be, more of the style checking, consistency, how we write things, maybe what features we're using. This is actually going to be, when we return from the exam, we're going to practice with some of these tools here. There's a handy tool called CPP check, which will try to predict if you have any errors in your program. We call that a static test or a static analysis. Maybe some folks who have used or been using IDEs like CLine, right? You have a tool called a linter that might say, hey, this variable is unused, or sometimes it'll point out different errors that might show up. But those tools, their job is to basically check against a set of rules that have been pre-written that a bunch of programmers have just agreed, hey, this is a good idea if you initialize all your variables, right? And it'll look for that consistency. Or, hey, all of your class names should start with a capital letter, right? So those are things that tools can automate. And if you don't do that, you break that convention, that's seen as a warning or an error, right? Because your code's communicating something, and whether you're using lowercase or whatever, could cause problems down the line to the next programmer using your tool. Another part of this, it's sort of built into the language. It's actually a nice part of C++. I know C++ again has its sort of pros and cons, but the type checker that we use. So when we say something is an integer or a float, that's a type of static testing as well, right? And we saw when it was in the last lecture, we had pi and we declared it as an integer. We want to be able to capture that even as a warning and alert us that, hey, that there's a type mismatch here, okay? Often things can be implicitly, that means just sort of automatically converted to different type, so it works. But usually we want to know about that, okay? In C++, there is a keyword called explicit. Let me just capture this in some source somewhere here. So if I have a class here, I'm just going to call it number, and we'll have some public thing here. I can type in front of the function here, explicit, there we go, a constructor, and that it takes in an integer I, for whatever reason. And if I come down here and try to use it, and I pass in 3.1415 or whatever, this will result in an error. Okay, because we want to be explicit and say, hey, this is an integer. We don't want the compiler trying to guess, was this supposed to be a float or whatever. But again, that would be a sort of type checking thing. One of the antidotes I think I've given in this class, or at least at some point, a lot of Google's code that was Python, they're converting to C++ now, because this is really important that types just don't change randomly. Same thing with their JavaScript, right? You can get a little bit wild and just, something's an array. Oh no, now it's an integer, and then it's a bool, 3 lines later. So we actually like this sort of type checking, at least at scale. Yeah.
Does that work with asserting that it isn't null?
Asserting that this isn't null here?
Yeah, that so since you're putting in a float to an int, it won't typecast it. But what if you, and I don't think in C++ ints are nullable, but if you're trying to pass something else in, because I know in Java there's assert not null.
Oh, yeah, let me think about this. So you're saying, let's see. I mean, so this will error out. I need to think about, let's make this like a pointer or something. I don't know if it'll check, if I did something like this. I actually don't know if this will error out or not. So I think technically this would be valid. That is, pointing something. Yeah. So, yeah, Java has, that is nullable or something like that. So maybe Java's even a better choice. There's some things. Yeah. Okay. Let's see here. So that's on static testing. That's the first part of it. The second part is, again, sort of measuring, and these can be sort of metrics about your code. Places, again, like Google, for folks, I think we had maybe one person here who attended the Titus Winter talk, but they really care about what they call code health. So they've got a really big, Google's got a monorepo. I think it's several billions of lines of code. Some of it's automatically generated or whatever, but billions of lines of code. They want to know how healthy is it, how many errors are there, are programmers doing weird things, are there a lot of warnings, these kind of metrics. So this is the idea with the static testing. Wouldn't it be really feasible to just run software constantly, so you just kind of statically look at it? It's kind of like a spell checker in Word. That would be like your code health. How many grammar errors do you have, spelling errors, and so on. So one of the metrics folks will use sometimes is this thing called cyclomatic complexity. Okay, so it's got kind of a fun name here. But the idea is, in your code, it's usually a warning if you have a lot of deeply nested if statements or a lot of deeply nested loops. Okay, so I'm saying, the below is bad, because it can often just make the code hard to understand if you have to branch a lot and jump around. Okay, you have to think a lot. When it comes to testing, we might have to, our test cases are sort of exponentially growing, right? Every nested if statement that we have. So cyclomatic complexity tries to capture this in some sort of number. I forget what the range is, but it's some normalized value between 0 and 1. If you're really close to 1, that means your code's hard to read, or this block of code is hard to read. Okay, so just to again make this sort of concrete here. We would prefer if we had some code like this, I equals 0, I less than 10, I plus plus, and maybe you have another nested loop here. You're doing some sort of, I don't know, bubble sort or something here, some sort of comparison sort. This is pretty manageable, a loop within a loop here. Depending on how wild you get here, with some other things, just kind of exaggerate this. Actually, let's see here. If you folks give me 1 second, I want to show you a wild piece of code here. Let me hide here. It's from a talk I gave. Just gotta find it here. And I want you to see which one's better. Or I just want you to see in practice how many loops you can actually have. Because maybe you've never seen more than 2 or 3. At least if we're teaching, sorting and stuff properly here at Northeastern. You've probably never seen more than 3 loops here. Let's see. Hope you'll see me on the recording running through this, but that's okay. I want to surprise you. Let's see here. Oh, yeah, this will do. Okay. All right, so take a mental note in your head. What's the most number of nested for loops that you've seen? Let's see if this breaks a record here. Okay. It's a little bit small. Here, I'll make it bigger. Okay. And bring it to the front here. All right, has anyone ever seen 1, 2, 3, 4, 5, 6 nested for loops before? Okay, maybe one person here. This is a matrix multiply, so if you're doing sort of math stuff, this can be one way to do it. So I would argue that this is hard to understand. Right? We're probably going to make a mistake somewhere. Right? It's true, we only have to get it right once, but you can already see there's a outer loop here, I1 equals 0, J1 equals 0, K1 equals 0, and then somehow we come down here and we're setting I equal to I1, which is way out there. So there's a lot of wild stuff kind of going on here. And you'll see code like this. So you probably want to be, if I'm managing a software project, I probably want to be alerted if all of my programmers are writing code like this. Because if they write it like this, okay, it's a little bit wild. But what happens if they leave, some other company, fix them, and then I have to maintain it? Uh-oh. Or we have to hire some engineer, and they say here in an interview, well, yeah, you want to work at such and such corporation, here's, our lovely code base. Have fun. Right? We don't want this. So, this is no good. So maybe I can, actually, let's just paste that in here so we have it forever here. All right. So remember what we will try not to do, unless there's a specific, has to be a pretty specific use case for that. In that case, that's a talk about doing matrix multiply very efficiently. Sometimes you do have to do it, but you better know why. And there's no comments in this code. Okay. So that would actually be another metric that you might want to report on statically. How many comments do you have per lines of code? I don't think, or maybe GradeScope or some of these other tools might have that, or you might get comments on it. But it's something I generally try to look for. One comment to one line of code, might be a good metric. All right, so that's static testing. Okay, so those are sort of our verification techniques. White box testing, black box testing, and then doing some static testing. Looking at our code, relying on our type system, and so on. Okay, so the other half, though, of our software testing, so beyond the verification, goes into the validation section. So during the development process or at the end, what we want to say, again, does this meet our expectations? So again, this might be our paint program. Maybe we run it, and every time it's supposed to generate a really pretty picture. Okay, does it meet those specifications? So how do we do this? Well, usually we have to use some of these other techniques. So the first that we could use is formal methods. This is something that actually Northeastern as a research university is very well known for. Probably, you could argue top 5 in the world for some of these things. Maybe number 1 in some categories. But sort of mathematically proving beyond a doubt that your code is correct. Okay, so that would be an exhaustive test. Code's never gonna fail, which is a pretty cool guarantee to have, especially if you're working on a safety critical system. Okay, so this is where the math, for those who are more math inclined or want to take that path, learning some formal methods while you're here at Northeastern. The second is a technique called fault injection. So this is, again, while the program's running, you say, okay, it's passed all the tests. We're pretty confident it's going to work. But what if when it's running, I try to break the program? You're being the sort of adversary or the difficult user trying to cause or insert chaos into the system. Okay, and that could be at the software level. Could also be at the hardware level. So again, folks might have to really think about this. Again, if you're NASA and sending a satellite into space, you might think about, well, how could I test what happens if a satellite is there for 20 years and is sort of eroding, if it gets hit by, other space junk or whatever, will it still work? Okay, so that's going to be kind of extreme, fault injections. And then the other is dependability analysis. So it's looking at your software and saying, okay, our software is running, there's a bunch of moving components, but what if you get a Windows update in the middle of whatever you're doing and it changes? All right, does that break anything? All right, so just looking at these, again, a little bit closer, our validation techniques, formal methods. Again, this is sort of mathematical proof. For this class, it's not really going to make sense to go into that for the type of application that we're working on. But again, it's this idea, some folks might be interested in this, that you can take some sort of code that you're writing, assign it to symbols or what's changing, and try to have a proof that it'll always resolve. I suppose is one way to say it. In this little example, they're just trying to prove that a value is going to be greater than 0 here. Okay. So again, depending on what industry you go into, this may be more or less important, and it may just be enlightening later on just to check out one of these classes here at Northeastern. All right, fault injection. So entering errors into programs just to see what happens. So here's a program. This time I happen to own the source. You don't have to have the source. You can inject faults other ways to make your system behave sort of strange. But all I'm doing here is I'm taking as integer inputs some value from the user and I'm calling our famous square function. But then I say, haha, what would happen if I instead said our input is the letter A? Okay, I could start trying these edge cases and seeing, is it going to throw an error? Will it actually just interpret that as a number and give you something back? So that will lead you to sort of say, okay, that doesn't meet our model. We're not supposed to handle characters, so we should, throw some error, exit the program, return something to the user. We have to be able to handle this somehow. Oftentimes, rather than modifying your source code and just putting in, random letters or whatever, there's another technique called fuzz testing, where you basically just say, hey, I've got a program like that, and I'm just going to throw a bunch of essentially garbage inputs into every function that takes arguments. Compiler developers actually use this a lot, because if you think about the space of all the different programs we're going to write in C++, they just want to see what generates an executable, essentially, and what won't. They call that the fun name, fuzz testing, because they're not trying anything really specifically, they're just being really fuzzy about it. Okay, so the other software validation technique, dependability analysis. So this is basically looking at your code and saying, okay, I'm making a bunch of calls to some third-party library. What happens if there's a bug in that third-party library? So for that's SFML. What if it changes or there's an update that happens? Then we maybe get a crash on some specific functions. Oftentimes, if you're calling into some API that's using, say, the web, calling into the GitHub API or Facebook or whatever, and it crashes, then what happens? Is your program 100% reliable? Can it do something else? Does it report an error to the user? What happens? Is it timeout? That's what we're trying to figure out here. Where are your dependencies?
So do we actually kind of like provide the expected output from that library as an input?
When you're testing, you mean? Or? Yeah, so for instance, if I'm testing for this, I might try to figure out, some CAN data. So in this example, I'm just connecting to some client server, some network thing, and I just want to see if that resource is available, connect to it, and otherwise, print out connection error. So if I was just testing this, I would assume the connection happened, populate with some fake data, and then sort of go from there. Yeah. So you have one test case for what happens if it works, and then one if it doesn't, and how do you handle that? All right. Has anyone ever seen Jurassic Park? The 1995 one? Right, Samuel L. Jackson, before he was big. Right. So if you haven't watched this movie, it's a great example of dependability analysis. In terms of people, I guess, where if the one guy who knows what's going on leaves or goes rogue, do the dinosaurs all get free? He says, hold on to your butts here. Alright. So summary of some of these, testing techniques. And they can overlap a little bit, but our verification techniques, our validation techniques here. Okay. So our black box, white box testing, static testing, just looking at the code, and then maybe more formally proving something, intentionally entering errors, and then maybe trying to figure out where our dependabilities are. Okay. So now let's put them into practice here. Figure out, how do we test these things in C++, or at least give us a few tools here. Okay, so some potential ways that we can test in C++. These are sort of the built-in tools. Okay? We can just print stuff out. We can sort of write these sort of ad hoc tests, a bunch of conditional statements. And then, again, most folks here have been through Java, so we do have exceptions in C++. And we do have assertions as well. Okay, so let's just kind of look at these one at a time. All right, so our first testing strategy here. I've got a program here, one function with square here, takes in one parameter. And we test it out here. Int 4 equals square root of 2, and then I just kind of print out the value. A lot of folks think about this as a testing technique.
I think with this we are kind of changing the source code, which is kind of dangerous again.
Yeah.
So the last time.
Right? Yeah, from last time we learned not to do this. Not to just go around changing our source code. Probably not good. Probably not, very sustainable. You have to look, with your eyes to see if the test passed very clearly. And of course, this doesn't really scale very well, right? So this is, pretty obvious here. Probably a good sanity check to do every once in a while, but again, we can do this in our debuggers. So let's improve it a little bit and use our actual programming language, right? So this time we actually say, okay, if this happens, or it's not equal to 4, that's probably even better, then print out what the result was and then exit underscore failure. So that's just the C++ way to sort of exit and signal that there was a crash. Your program will return 1 or something. So this red might be a little bit harder to see, but this is exit failure here in all capital letters. What if we think about this? Better than before? A little bit better. Okay. Yeah. It's essentially the same thing, though. We're getting better, but again, we probably don't want this in our main code. Writing all this in here, our test cases. Okay, so as you've likely done for folks who took OOD, and then maybe other folks in other classes, we want to break this into different tests, okay, different test cases. So typically we call these unit tests. So I have the same code here, or the same logic, just checking, if square of 2 is not equal to 4, then, return something, give us some information. But I've just broken it out into functions, returning true or false. Okay, to supply with me some information. Okay, so that's going to be the idea that we can get some, information back by having either these individual tests or maybe embedding some more items here. So this is better in the sense that we've broken out some sort of repeatable block of code here. We've still got this embedded into our main function, so we're probably going to want to clean that up eventually, though. And I'm actually going to demonstrate our testing framework so that we don't have to, in our application, have these unit tests somewhere. Okay. And again, folks who have used Java, again, I'm not a huge Java person, but you've probably used JUnit or these sort of frameworks for this. Okay. All right. So again, we probably want to improve this. This still also isn't a very good unit test because we always want to test the edge cases as well. So just really quick, what would be some other edge cases that you'd want to think about? If I was just trying to square a number. What was that?
Negative number.
Negative numbers. Yeah.
Whatever the square root is of max int.
Max int. Yeah. So max int, uppercase max underscore int will give us the biggest number, right? So we could have overflow. If it gets too big, what do we do? Do we handle that? Actually, how do we handle that? Does anyone know? It's a good interview question.
Like in this specific situation.
Just how would I know if I did something to two numbers if I got an overflow? I've been asked this on an interview. That's why it comes to mind. In graphics, we do have to worry about this.
Doesn't it usually turn negative?
Yep. Yeah. So the result of two numbers, if we get the opposite sign, if we're doing like an addition, then we get a negative value back. And then there must have been an overflow. Yep. Yep.
That's
Right.
about let's say with like a two's complement, that's it.
Because of the two's complement representation. Yep. Yeah. So all that, I don't know where we learn in discrete math or whatever. It's like, oh, it's coming back. It was useful. Two's complement. Usually we don't have to think about it, but on occasion. Okay, so yeah, I like that sort of the, a couple of these edge cases here. Always, illegal, floating point values, negative. I actually don't have the overflow one on here. Let me put that in here. Max int and min int. That's what it looks like. Okay. All right. And I have another question here. Are there any limitations on our unit tests? Only have one. We could write another. I guess I could either have if square, test a bunch of them here, or separate this into multiple functions. But what other kind of limitations could we have? Yeah.
It's usually not feasible to test the whole problem space.
Yeah. Right. So we probably can't test. Well, let's see. The integer is what, negative 2 billion to 2 billion roughly on our systems, 32-bit integers. So feasibility. So we have to pick, good edge cases and just rely on it working. Right, that goes back to the Intel floating point bug where, some of the floating point numbers, I don't remember which ones, just didn't work. It's like, yikes, how do you find that out? If you just happen to be unlucky. Right, sometimes we also have, it can be a little bit tricky. This is actually going to be something we have to think about on our unit tests for our painting program. This will be in assignment 4, but how do we unit test, user painting? We'll have to think about that a little bit. That'll be part of your next lab and homework.
I think it will even become even more difficult the more strongly coupled the programs become.
Yeah. Oh, this idea about how coupled our programs are. Yeah, I'll give some a hint what you'll be doing for homework 4. So if we have a singleton, can I write a bunch of unit tests with a singleton very well? Probably going to struggle a little bit, yeah, because we have a lot of state that our code's very coupled. Okay, so we'll have to do something with that. Yeah. Okay. So, in general, unit tests are pretty good, right? This is sort of going to be our de facto or go-to. I don't think that changes. I think this is pretty, standard practice in industry. Still a useful tool. But again, we probably can't do everything exhaustively. We probably can't always mimic the system. So, for example, if I'm testing Google, at scale, I probably can't do that on my machine. I need a server cluster to do that. Maybe my machine is different than what the user's is, different operating system, these kind of things. That can actually be a good thing to develop on a completely different machine than where you're deploying. But you still have limitations. What libraries are available? What you can test for? How fast is your processor? All those sort of things. All right. As an aside, unit tests can be super useful too for project managers. So I don't know if everybody here wants to go straight to software engineering if you're sort of more on the production side, but usually you'll get one of these dashboards and kind of see your code health and how your project's doing, how many tests passed, these kind of things. So we'll have a little bit of feedback in our testing framework as well. And that's why unit tests can also be helpful. All right, so another testing strategy we can use is exceptions. Okay, so just like Java, we can have our code executing, and then at runtime, if some error happens, we can try to handle that error without just crashing our program. Okay, so in C++, we just have try and catch. There's no finally like in Java. That goes against this RAII principle, meaning that if I just try something here with some object, I need to be able to clean it up if there is an error. So that's why we don't have try, catch, and finally. But here's sort of the simple example of an exception. I have a try catch block here, and then I can just create an exception here. Then the keyword throw the exception E, that's the thing I just created. And then catch ... just catches any possible exception that occurred. Okay. So that's the syntax for that. ... Now we can catch specific exceptions as well, just like in Java. So if we have some numbers here, so I'm trying here, I say if b equals 0, then I throw an exception here. This is divide by 0. Then I can catch a specific exception for that. Okay. If I want to handle whatever the data type of the exception is. Okay. Yeah. Question.
Why, in this case, does it catch case 1 but not, or it catches case 2 but it doesn't catch case 1?
Yeah, let's see. So I have B here, throw, you cannot, oh yeah. So the exception that I'm throwing here, let me make this a little bit bigger so folks can see. It's a little bit silly here. What I'm throwing here is a string. That's a constant char, that's the type. That's what I'm actually throwing here. So we're going to get exception case 2 here. Because I'm literally just throwing a string.
So
a constant char string.
So if you declare a char array, and then through the char array, it would go to case 1?
Yeah,
Okay.
yeah, exactly. So it's whatever the type is of the exception that we're catching. Yeah, this is a little bit nuanced C++ here.
I
Yeah.
have a question. So if you're kind of using char star e, so you kind of do return char in the function, right?
Sorry, what was that?
Like usually when we work with the strings in the functions, we can just simply return their name.
Mm-hmm.
Like I can just simply return e and it will return the complete string.
Yeah.
So if you're not using it as a constant, so can you kind of do that?
Yeah, I mean, typically, this one's a little bit weird where I'm just throwing, this particular type. Usually we would just create exception E, and then just throw E. What we're gonna do in lab today actually is create your own exception type, and we do that by just inheriting from the general exception C++ exception class.
No, but my question is like in general, like when we work with the strings, right?
Yep.
So in this particular case, it actually went to the case 2, which means that it was treating it as a string and not like a character array.
Correct. Yeah. This is creating it as a constant character star, not as because a std string is not a default C++ type.
Yeah, so I'm asking that when we actually like write functions where we want to return strings.
Yep.
So we like need to use like the const term there, right? Or otherwise it will just be pointer to one single reference and not the complete string.
Yeah, I think for this one, if you wanted to handle the string case, what you do is, let me go up here, is you would just say, okay, I have some string, my string, and then you would throw my string like this. You have try, throw the error, and then your catch block, you would handle the string case here, like this, for that type. Does that answer your question about just how to handle, if you're like just returning a string type? Yeah. Oops. Just leave that there. Alright, let me undo that. Alright. Okay. Now one of my questions with exceptions, we use them a lot in Java, and I wonder, I wonder how you learn about this, but why not just use if-else blocks? Why are we going through the trouble of throwing exceptions? We're essentially doing the same thing, right? We want to say if, run some code, if we get some error, return. Yeah.
Because if you're like writing a library or an API, you can throw exceptions out of your methods, and then somewhere else in like client code, they have to check for those exceptions instead of just checking. Because if else is really hard to check some exceptions.
Yeah, right. It gives us a lot of sort of enforcement in our API, right? If we can catch an exception for that type. It's a lot cleaner. We sort of can contain versus saying, well, you should handle error code 1 through 17 or whatever this function could return, right? It's a lot more difficult. Okay. So typically, exceptions in C++ are a preferred style. Depends what domain. If you ask me when I teach game engines, I say don't use exceptions. There's reasons for that. Performance most of the time. And most of the time you just want to log and then just crash is fine in that case here. Okay, so, and again, this second part, right, we can handle the actual errors, wrap them and package them up into a nice object, and then sort of serialize or send out that exception somewhere to handle it. Okay?
So do you have to like write several statements in the end?
Most of the time, we just don't use exceptions, for performance, because they're considered these sort of heavy things that are carrying a lot of state with them about all the error that happened and all the potential sort of use cases. So these try catch blocks are expensive. There's a few of the reasons in here summarized. So again, this would be an example of if I asked about this on the exam, they could say, well, Mike said, or I've worked as a game engineer, and we don't use it for this, X, Y, and Z reason. Right? Defend yourself. That would be fine. All right. So our fourth testing strategy is assertions. Actually, before I flip to it, does anyone know the difference between assertion and exception? How would you sort of explain this if it was a job interview? Yep. The interviewer comes up and says, "What's the difference between an assertion and an exception?" What would you say to them?
It just crashes the program assertion.
Assertions just crash. Okay. Yeah. Exceptions could crash it, I guess, if that's how you want to handle the error. Okay. Yeah.
I think it's good just kind of for the comparison, like is it one rather than like except to actually throws an error and crashes it.
Yeah. So you're both right. Yeah. Assertions are just gonna. It's a very strong statement, and it's just gonna crash the program if it's not true. So you're exactly right. The exception could as well, but we have a chance to handle it. So, assertions are very strong statements where we're sort of saying, hey, if this thing doesn't hold true when our program's running, something really bad's happened. So we've just got to crash. Assert itself in C++, there's no keyword for it. It's a macro. Right? We learned about what those are, so it's going to expand out into something. We just assert 2 + 2 = 4. All is well in the world. If it doesn't, then we want to crash our system here. Okay. So usually we like these. Again, you might have asserts if you're building some data structure and you want to assert that it's not empty, for instance. So that could be a common reason if you're going to perform some sort of operation. You'll have to decide if the appropriate thing is to crash, depending on the domain you're in. But this is a use case of assert. Common, question.
Can you catch a failed assertion, like in a try-catch block?
Not really in the C++ way. What you can do, and basically the way that exceptions are implemented is at the systems level, your operating system's giving you some signal. So right, we saw this with segmentation default, SIG, SIG, EV, or whatever it is. You can handle them at that level if you're in sort of the operating system, but it's still sending a sort of kill instruction to the process to turn it off. But you can you could override some of those and maybe make it do something different. Yeah.
Thinking from like a user perspective, I always feel like why do you use assertion? Because if you're using some application in your phone, right, and you might not want it to completely crash, rather than it should give you some message why it actually crashed.
Yeah. So we can get a little bit of information out of asserts here. So how we might write them. Let's see. Let me go down here. So it's usually an include C assert. And let's assert 2 + 2 = 4. So that's usually what we're left with, and then it'll crash. But you can do this little trick here and say 2 + 2 not equal 4 for some reason. This will, when the machine crashes or triggers this assert, it'll give you a little bit of information. So that's a little trick you can do in C++. But yeah, this is where you have to sort of make the decision if you say, hey, this is an iPhone app or Android app, and maybe we'll want to handle this error. We would model this to catch an exception for some integer, and then do something.
I think usually this is the point that they ask us to send the report, right?
And then send an error report, yeah. So my advisor in grad school actually knows the person who gets those reports. They do go somewhere. He said he gets several millions a day or whatever, and they have to get filed. They eventually work their way through the system, but I was like, wow, they do go somewhere. To send or not to send doesn't matter. So we got to meet this this poor person getting all these error reports. I hope they're getting paid well. So. All right, so in C++ we also have static assertions as well. So remember, we think about the language as what we do during runtime, so catching exceptions, assertions, and so on, and also compile time. So this is an example if you use static _assert, and this is a typical use case where you would use something like this. They're a little bit harder use cases, but you might say, hey, is the size of this void star is just a pointer that can point to any sort of type? Is it 8 or is it 4 bytes? And I want to check the size of that so I know if I'm on a 64 or a 32-bit system, right? Because you might need to verify. You wouldn't have both of them here typically in the program, you might say, okay, it must absolutely be true before I run this program. I'm relying on it being, pointers or 8 bytes or a 64-bit system, and maybe that changes the behavior in some way. Okay, so you might have these sort of flags here. Okay. And some of these are things you build into your build system, and then you say, okay, if it's not this, then recompile and build, but assert, it's 4 bytes or whatever. So those are just some of the use cases. All right, and just as an aside, there is a C++ 20-ish feature. I say 20 or C++ 20, 23, because I think they took it out and they put it in. They keep taking it in and out. But you can also write these sort of contracts in your code as well, where you say, okay, hey, I've got this multiplication function, and I'm expecting x must always be greater than 0. I'm expecting y also should be greater than 0. You can sort of write these guarantees. So this is a new thing that's coming. People have decided this is a good idea to have contracts. Depending on other languages you may have used, you might have something similar. But this is actually something that came out of research, and they said, hey, this is a good idea. Right. So you might again have things like you expect, if this is a division function, y is not equal to 0. So you never divide by 0. Okay.
So is there expected behavior more like an exception or an assertion?
This is more of an assertion. Yep. Yeah, to encourage people to write, assertions. And these will be the same things where you say, okay, I've got this, and then in my consistency checker, and in that test, you check all of your functions have a contract that states something. Yeah. Alrighty. Okay, so when to use either of them, assertions or exceptions. Assertions are stronger, right? Those are going to crash the system. We're saying this is something that absolutely must be true. And usually you're using them to verify inputs or some sort of input data type that says, again, if this isn't working, crash your system. And again, if you're sort of asserting something in a complex system, right? Maybe you crash and then restart. That's the best thing to do. Right? Exceptions usually handle sort of external input. That's you want to handle the exceptional case, right? The user is doing something weird. They're trying to divide by 0. And you say, well, I didn't want to write the logic for that, but I can handle that case, throw an exception, catch it, and then, we can still proceed. But we don't want to handle, we don't want to crash our program. Okay, so you want to keep things running. And then I say, in general, you want to liberally use these things, unless you're in a domain where it's not appropriate. Something where performance matters, error control system, maybe where you can't be slowing down the system with some of these things. Games, again, would be another example. All right, let me pause there because we've been going for a little while, and let's get our break in here for about 10 minutes. How about 7:35? We'll resume, then we'll see some of this in C++, and we'll keep going from there. Let's move our break thing here. Yeah.
I have a quick question about the GitHub for this.
Yep.
So is it attached to our GitHub, like our personal GitHub, or is it attached to the Sissy app?
Whatever one you signed up for, which is probably your personal GitHub.
Okay.
Is that why you can't find it, or?
Yeah, I couldn't find it.
It might be kind of hidden.
Huh.
Okay. I can look you up too if you have your username.
Sure.
Actually, The other way to do it is if you just, oh yeah, I disabled it. Sometimes people get into it like strangers on the internet. I'm like, what are they doing? So if you type, here's the URL actually. We'll just copy and do this here. So it'll be whatever this is and hyphen your name. GitHub.com / FS fall 21 FSE hyphen. Yep. Perfect. You're welcome. Thanks. Yep. Yeah. Hi there.
Hi. So actually, I got to know from one of the VAs that my mini paint assignment is not. He cannot run it, and he said that I should probably get in touch with you and you'll be able to do it.
Okay.
Yeah. So.
Okay. Probably after class, we'll take a look at it.
Yeah. Sure. Thank you.
Hi there.
Yeah, actually I want to discuss with the assignment 3 that the around static methods, because I just found questions on Piazza that says it's better to use a non-static the add method, add and execute, and it said that because we don't want to affect all the commands. I just don't see the reason here because the commands are also in a static container, right? They're always there, so every instance could access them.
Yeah.
But why have we?
I'll have to look at my Piazza thing to see what I said here. What did I say? Did I say not to make it static or something?
Yeah, so someone just asked why we're not using the static method.
We could. We certainly could do that.
Yeah, because others members are all static.
Yeah.
I just don't know why we have to use the exception here.
We could. I don't think it's gonna throw any error here. We should probably make it
Yeah,
static.
no error. I just changed into non-static, but all the static works well.
Yeah. So all static should work fine.
Yeah.
Non-static. I'm trying to think of a reason why you want it. Because if it's a singleton, you have the general just to make all of them static, because all the static ones can access your static fields. And then all the members are static. Yeah, that should be fine.
Yeah,
So,
if I have to use a non-static method, then I suppose other members maybe they should not be static.
right. Yep.
Okay, and also there's some. I tried the refresh thing, like using the clock class.
Okay.
Yeah.
Oh, for the refresh rate.
Yes,
Yeah.
the refresh rate.
Yeah.
Like I update them in here. I get a clock and get the elapsed time.
Yeah.
To just check this, but I put this in this outside draw function. But what if I write this condition inside
Probably update.
inside the loop?
Yeah.
Yeah. What if I write this condition statement inside the loop
Yeah.
function? Then it just cause there's error, the non-plus type error.
Oh, there's some error. Maybe it doesn't know about
I
the
really-
clock
Yeah.
function. You have to include SFML there or
Yeah, I
something.
have to include the clock function here. Otherwise, it just crashed.
Interesting. I mean, it might be missing whatever SFML headers there. If it's just crashing, that's probably something different. Is it giving me a syntax error or is it crashing?
No, it's the non-class type error. Like
Okay.
you can't use this function, these two functions, the get time and the restart.
I think it's probably just missing the SFML header file there
Okay.
in app.cpp.
App.cpp.
Yeah.
Can
Can you run it and move it in there?
It's a little hard.
Okay, yeah, maybe we try
Yeah.
after class and we can kind of debug.
Okay, I see.
Yeah.
Yeah.
You're
Python, in class with other languages. In the past, there was, we didn't do drawing we did one with like a remote control, right?
Uh-huh.
So each button makes a new command. The command only has one method. Actually, that's it.
Yeah.
So it was pretty. Well, that's how my brain is wired now. So when I see draw and undo, I really want to create two commands. Like draw should be one command, undo should be another command. But in your template, you have execute and undo and redo and everything in draw.
Yeah.
So I can't rewire my brain.
Okay. I mean, think about it this way. Right, so, I mean, when you have like a controller or whatever, you know, I think the example that they give here is X, whatever, triangle, square, circle. You know, each of these maps to some command, right? You have the X button, that's just some pointer to some command. Right, so I can point this to whatever I want. So it sort of makes sense that every command that I have has a dot execute or whatever.
Yes.
Right, press this and it executes. But that doesn't mean that I can't hold extra information inside of this class here, command. Okay, so if I have command here, right, and then I do have execute. But you can sort of imagine this if you want to sort of rewire it right on a PlayStation controller or something, you have like the option button. So what if I press the option button and X at the same time? Then I want to do this other function, undo, which is just the opposite thing there.
So that makes sense. So let's say I click the Z button.
Yep.
And I say, when I click the Z button, put in your code, I should create a new command object and then type it into the app.
Yeah.
Now, is this command object also draw? Like, I don't have any. Should I create my new command?
Yeah. So you have draw here, which is a type of command.
That's all I got. Yeah.
Yeah.
Are we expected to create more?
Eventually, right?
Oh.
Maybe we'll have more.
Oh,
Right. So right now this is handling every time you left click. Right. Just think of left click as pressing the X button.
And Z.
And Z, right? But
Should Z actually create a new command? No.
All Z is doing is every time you're hitting X, your mouse is populating, command in some structure.
Oh, so then Z, pressing Z should just look at.
This undo, or after we're done with that, this undo or whatever.
Okay.
Right, so it's just walking back through this data structure and saying, well, instead of every time when we put something in and we're executing, we're just walking, backwards in our data structure and doing undo.
I don't actually know how to access that because it's so.
Well, if this is in some data structure, let's say we've got an array of commands here. Let's just say you've got an array of 10 of these. Right, I can do command at 0 dot execute. Right, that's what we did as soon as I hit X.
What I mean is.
I can also just call undo.
Yes. What I mean is, getting from main to this part.
Yeah.
I'm trying to understand your template. I actually don't know how to get from main to this part when I want to undo.
So you have this data structure, wherever this is,
Yeah.
in your singleton.
Yes.
This lives inside of app.
Yes.
Right? Since app is global, you can do app, whatever. Add command,
I've only got that.
execute command. I think you've got other things in there.
I don't have app.undo or anything like that. Because undo lives inside what all I've got is draw. App only is sorry.
Let's see what
only
you
is
have here.
inside draw.
I think you've got. Let's see. I'll tell you exactly what you got here. 3.
I'll talk after class too.
Yeah, just. You do have execute command. Yeah, I mean you can add. Why can't we add undo?
because undo already lives inside draw.
Does it?
Yes, according to your.
Draw is a type of command, but we actually have in our app all the commands are being held there in a data structure.
I know this. Can't wrap my head around the template.
Yeah, I'll try to look at app. So just looking at this, right? I have here all of the commands. So every time I do something, every time I press a button, I put a command inside of this data structure.
Yes.
So I have it right, always here.
Yes.
And then when I want to execute, I mean, I can just walk through this data structure. Forget executing for now. Just every time I click, I just create a new command and sort of populate this data structure. And then when I'm ready, I can just walk through and then start executing these commands.
Yes.
But I can also walk through and just doing the undo as well.
But
Let me let you think about it.
I've already thought about it for.
Well, think about it now.
It's not this. It's how do I get from main, which you said I shouldn't just do my entire application main. Like that's not the correct way.
Right.
So so main should only do certain high level stuff.
Right.
And then I don't know how to get from that to here, correct?
Okay. Well, think about the app singleton. We'll let me get started back in class again, but think about the app singleton because that's where you have access to everything.
Yeah.
And then your stuff that you have. Well, you get to those sort of free functions that are in main through the singleton function pointers, I guess, to say. I'll talk about this after class or in the video tonight. That will be filmed. Yeah, but you're almost there. Alrighty, folks, let me get us back in action here to talk about testing. And something to think about here. So we talked about some different testing strategies, techniques, some of our tools. And, I agree, unit tests are probably a good idea. But how do we write a good test? What does that mean? What are folks' sort of thoughts on that? Yeah.
Each test should really only cover one specific case. It should try to test multiple things at once.
Yeah, probably, a lot of these unit tests are one-to-one. We could have some bigger ones, but yeah, we're trying to, make sure things work. Correctness? What else? Yeah, they should have some specific goal, certainly. I like that. What else is in a good test? Yeah.
Have clear results for if either it's clearly correct or if it's incorrect, it gives some sort of good feedback on what is incorrect. It doesn't just crash and nothing happens.
Yeah, so it should meet our specification, and it probably shouldn't just give us some error code and hexadecimal or whatever. That might not be very useful. I mean, maybe it is, but we want to know if that's the right thing. Where we need clear feedback. I agree with that. Make it sort of readable for us. What do other folks think? Anything else? What else goes in good tests?
Depending on the requirement, thinking more in a bottom-up approach.
Okay.
Writing a very specific, a smaller thing first, and then adding the concurrences to
Okay, yeah. So starting small, building up,
Yeah.
a bottom-up approach. Okay. Yeah. Right. That probably makes sense too, especially in our test suite. Right. If we just build a really big test, which we can do, but then we have a lot of moving parts. So how do we know if that's right or if that breaks? That's kind of tricky. Yeah.
So that's why I usually write my high priority ones first.
High priority ones.
And then start moving on down the lower ones.
Yeah, so if we know a piece of code is going to get exercised, a lot more than another piece, probably make sure that one works. Or if it's more critical, trying to think of a critical system, a car or something, probably unit testing. The brakes is probably more important than, Most everything's important on a car, so maybe that's some good example.
The radio.
The radio, yeah. Maybe the radio. What was it?
Seat warmers.
Seat warmers, yeah. Although we don't want them too hot or too cold, I guess, either. So. Yeah, but yeah, there should be some sort of priority, right? The same thing we did in our user stories, right? We sort of had high, medium, low, or however we want to do that. You know, and this could be for how often we exercise our code, right? And we can actually measure that. So, you know, I think folks, you sort of hit all these here. You know, tests should be correct, meet our specifications, right? Usually starting out kind of small, building up here. We want them to be readable. You know, sort of testing the easy cases. You know, being kind of exhaustive, right? Or as exhaustive as possible. Probably can't test everything, but picking good corner cases. Sometimes our tests can also serve as documentation. This is another sort of tip, you know, as we're learning about navigating big code bases, right? Someday you're going to go get a job, and likely it'll be on a product that already exists, and they're going to say, all right, dive in, you know, it's a 1,000,000-line code base, and you're going to try to figure out how the different pieces and parts work. You can look at the tests, right, as a little example of, okay, how's one piece supposed to function? So demonstrability is sort of important here. And then, you know, our tests themselves should have some sort of resilience, meaning we can sort of execute them in any order, they're not going to crash. This is the one that's actually going to cause a lot of problems with the singleton for changing state frequently. All right, another question for folks. Do we include tests in our commercial code? What do folks think our test suite?
Like, do you publish the tests? Or do you test commercial code?
I will say, do I publish the test so, you know, when you download, you know, Mike's game or whatever, you also get my test suite? Probably not, yeah. You probably don't care, right? Yeah.
Sometimes like how we have like a small test just to make sure something's running.
Okay, yeah.
Really just, it's like you should be able to meet this, otherwise it's the software or your system.
Okay, yes. Okay, so this is actually, we probably don't give them all the tests, but actually in a game would be a common example where you run a little test that says, okay, does your machine have a powerful enough graphics card to run it? Or a little test suite. So yeah, probably not all of them. But yeah, sometimes there are cases that you know, test out a little bit of the product to make sure it works. So again, typically we don't do this, right? And we have seen some tool where we can sort of use our preprocessor to conditionally have, you know, our sort of debug statement here to enable or disable tests. And usually the consumers don't get that, right? Now, this still does leave some room for error, right? If I accidentally, you know, the last build that I happened to do, you know, I hit up on my arrow key and it happened to be a, you know, command statement for, you know, building, you know, the debug version. So there is still some room for error here. Again, we'll fix this with our CMake in a moment.
With the GTA game where we have those cheat codes that we
Yeah, right. Yeah, so this has famously happened in various games where you get like the debug version, which have like consoles and cheat codes and stuff. And then, right, you have the debugging symbol, so you can see what's inside the source code. This is really bad. So yeah, typically no, we try to avoid that.
also have a question about like your point on resilience in the last slide.
Yeah, resilience.
Yeah. I mean, like, sometimes when we are actually like doing the stability test, we want like the test cases to fail.
Okay, so meaning you want the test cases to fail. So what you're exercising
Like
in the
mostly
software?
when we're like testing maybe like SOCs, and then we actually want the test case to like fail, like we want it to like go on like multiple iterations, like more than 100,000 or something like that. So that we know like where the breakpoint is, right?
Oh, sure. Okay, I mean, yeah, I guess that's sort of like a stress test
Yeah,
to see where it breaks. Okay. Yeah, so there could be, if we call this a resilience test, how much can I throw at it before it breaks? I guess that would be, a different kind of test. We don't really talk about stress tests, but, I guess, I would accept that as number 6, depending on what type the test is for a stress test. I'm trying to think if I've done any examples like that where I want to see the breaking point.
I actually did it in like my co-op, in my internship actually. So we were trying to like, so I was working like on chips, so we were trying to find out like, if I run this AI model, so like what will be the breakpoint, like when the chip crashes or like when it does not receive the network or something like that, you can't make a phone call with the same model.
Got it. So just for other folks, like doing an AI project and trying to figure out where's the breaking point of something in the computation, right? Where are the limits? Yeah, so sort of a boundary test. Yeah, absolutely. Did you have a resilience?
I was kind of saying, like, I mean, like, I've also had to write tests like that before, but what I did was I just pointed it to a point where it would actually directly crash.
Got it. Yeah, so this is almost like our ready test almost, where we could just sort of, you know, run through this area and say, okay, how far do we go in the red zone here before it crashes? Now this is different for everybody's system, but same idea here, just kind of pushing it. Although your guys are more interesting than the array one. Yeah, cool to see this. Yeah, anytime we can bring stuff in from co-op, I love hearing about this stuff. The slides will get updated. All right. Now a few other testing strategies as well, and these will be very likely ones that you'll go through. I mean, you'll be doing this in your teams in this class, but this first one, code review, which is more of a peer evaluation, or maybe somebody more senior is going to look at your code. In a sense, they're almost using the scan and look technique to first look over your code and see, does it meet the style, does it look good, before you, move on to the next stage. So this could mean a lot of different things at different companies, but usually it means somebody sits down and says, Mike, I see your code here, looks good to me, go ahead and push it, and then, run the test suite on that code. Okay? The other sort of tool, and sometimes this is just I should say this is really its own, when we talk about software development life cycles, methodology where you write the test first before you even exercise any of the application code, right? So we call this test-driven development. And that's often a tool to ensure that we have a lot of tests to exercise different parts of the system before we even think about the application. So this is a big part of Northeastern. Actually, write the test first, then write the code, and have confidence that the code works. Okay. So code review, just a look at what that is. It's supposed to be a constructive review of a teammate's code. Kind of a key term there. Something we want to think about when we're working on teams. Talk about a way to make your coworker angry at you if you're doing a code review and you say your code looks bad. That's not constructive, right? Be polite. Critique the code, not the person. They're probably working hard on it. So that's just a note about soft skills, right, to have. But again, we do these things sort of naturally, sometimes in automated, when we think about like spell checkers, giving a manuscript to an editor to review before something gets, a book gets published. Same idea here. And this process, again, depending on where you work, code review could be one person, it could be two, it could be upper management, there could be all sorts of levels to this. Okay. Just as an example for how we'll do this in Git and GitHub, typically what happens is you have something you call a pull request. So roughly 3 or 4 of you folks will be working on a team, and you'll work in your own branch, and then what you'll do is merge your code at some point. Okay, but in order to do that, you need to submit a pull request that says, hey, I would like to do this. And usually that triggers a code review. Okay.
Why is it called a pull request instead of a merge request?
That's a good question. Yeah. I mean, because we're merging the code.
Code into the main branch.
Yeah, pulling it into the main branch. Think about that. Yeah, I don't know who names these things.
I confused the crap out of me when I first did it. I was like, I pull code to align my changes first before I do any of this.
Yeah, I think merge request would be a much better name. I don't know. Somebody's got to know. At GitHub here.
You can create a folder.
Let me see. I'm actually going to just play the videos a minute. I want to play it on this other PC so I don't get any copyright violations or anything. But, you know, just in case you've never done this, just to show what it is, just do one volume test here. Okay, that seems reasonable. And let's see. Code review. Oh. Just 1 second here. A little bit louder. Okay, let's see what they have to say about code review.
Code review is crucial, and shipping high-quality code is everyone's responsibility. A pull request review on GitHub lets you combine multiple inline comments and an overarching summary into a single package that gives readers a clear and consolidated view of your thoughts and recommendations. You can start a review by adding an inline comment in the file's changed view of a pull request. GitHub gives you the option to add a single comment or start a review. When you start a review, GitHub marks all of your inline comments as pending while you are reading and reviewing the files in the pull request. When you're ready to share your review, click the Review Changes button to add a comment that summarizes your review. You can submit your review as a general comment, as an approval, or you can request changes that must be addressed before merging. And if a pull request's base branch is protected on GitHub, you can also require an approved review to prevent unapproved code from landing somewhere it shouldn't. This also prevents code from shipping with any reviews requesting changes. Reviews all show up in the conversation view of a pull request as unified discussions with links to their full div for more context. You can also see an abbreviated list of approvals and requests for changes at the bottom of the conversation view before the merge button. Use reviews on your next pull request. Collect your thoughts and share them with others in a way that helps them see everything in exactly the right context.
Yep. Alright, so there you go. Some tools you can use. You review and then you accept the request. You know, you can have some conversations in there or whatever. You know, if there's one, you know, really nice thing to get out of this course, it's actually to go through this process so you have a little bit of, you know, confidence during your first co-ops or second ones or wherever you're going, full-time jobs, just to, you know, go through this process and learn some of these tools. It's going to be a little bit confusing. So I think that's actually a nice value add from the course perspective. I wish I had done some of this stuff. I just had to pretend like I knew what I was doing in my first jobs. I'm frantically Googling. I mean, which I do anyway too. So but that never ends. All right. So the second part after the code review, you know, test-driven development. So I think we sort of understand this or done this in OOD or other stuff, but again, in the picture. All we're doing is, well, we start off here, step one, you know, writing our tests until we're happy with it, checking whether our test is failing or not, and sort of iterating. And then when we get to our application portion, we write, you know, only enough code to sort of exercise that test until it's not failing. And then we can move on and integrate our test, our changes to our application code, and then merge all of that into the full application here. Okay, and there might be, again, some iteration here where you're refactoring other code with your new changes and so on. But that's the idea and sort of a picture of what's going on in test-driven development. Right, the test first, that's going to change something in your application, edit the application a little bit, and bring those changes into the overall application. Okay. So again, here it is, just at a high level. You add a test. Run all the tests, make sure everything's still working. You know, sometimes tests interact with each other or whatever, but make sure they're all passing. Write the application code, run all the tests again, refactor the code, integrating your changes, and repeat forever. Okay. All right, so this question kind of comes up. Maybe I should phrase this: why is testing so important and hard? You could read it either way. Again, we've mentioned a few of these things. You know, exhaustive testing is just often not feasible. So a lot of times how people sort of illustrate this is they'll draw your program and they'll say, all right, this box here, and all these, pixels represent all the possible things that could happen. And you just draw some lines as the boundaries, sort of distinct cases that could happen. The user does something here, something in this distinct box. And the point is just to say, well, they got to pick out or sort of partition our program and pick out some of the edge cases that are interesting here, a little bit here, a little bit here. And that gives us enough coverage to have some confidence. But again, it's hard to pick out those points. Sometimes in our programs it's hard to partition it and figure out, how do we break our program into small pieces? How am I exercising all the functionality? These sort of things. Most often we can, test the various edge cases, off by 1 errors, positive values, negative values, 0 values, and that'll get us pretty far. But we have to think about some other things as well, just based off the domain we're in. Okay, so let's get into some defensive programming in C++. Well, that's sort of defense against the dark arts here. For folks who have seen Harry Potter, the movie or the book series, here's all the professors here who always, I won't spoil anything. But all right, so what do we want to do? Well, we want to try to avoid bugs in the first place. So sometimes that means, utilizing our language, right? Some of the best practices. So we learned about this thing, RAII. Again, this thing with this sort of terrible name. Resource acquisition is initialization. Again, just trying to do all of our memory allocations in the constructor and all of our destruction in the constructor. Right? That makes our code pretty simple. It's easy to create objects. We're not calling random methods to allocate memory. So that's just really a good thing. Smart pointers we haven't talked about as much. I want to provide some more guidance on this later, but if we're finding it hard to work with pointers, right, where we're getting things like segmentation faults, we actually can abstract around them, and smart pointers can help us not forget to free memory, basically. Okay, and something else we can do is another testing technique known as code coverage. And make sure that the tests that you do actually write cover the code that's actually running. So if your efforts are being put in the right place. Okay? Our code that is executing frequently is probably what we want to test. You're actually going to look at a code coverage tool in today's lab and get to practice that little sample. Okay, so this sort of resource acquisition is initialization. Again, this core idea here, just do everything up front when you construct the object, and then destroy everything when you destroy the object. That ends up avoiding a lot of bugs. It simplifies the design. It's easier to test for. Your unit tests don't have to have 100 things going on. This is a good rule. All right, so there's some more on RAII here, but that's the idea is right here in a sentence here. Constructor creates an object, a destructor destroys the object completely, all the memory. Okay, so here's the talk if you want more resources on it. Why this concept tends to get, thrown at us a lot in the C++ world is when we start to think about things like concurrency and locks and these sorts of things. So this talk actually, might provide a little bit more, encouragement for why this rule is important. Okay, a little bit more motivation. Smart pointers. Again, I want to talk about this specifically later on, but they're going to be a tool or an example of a tool just using our programming language to help us. Okay. This is actually next week. I'll be out of town as well while you're taking your exam, but I'll be talking about pointers and touching on these. So there will be a talk delivered in front of another audience, and then you will get access to that talk as well, because I'll be recording it. So the basic idea with these is we can create pointers that just clean up after themselves. We don't have to remember to delete or delete with brackets or these kind of things. Yeah? Pardon?
I'm sorry, so the exam will be a take-home exam?
Yes, yep. So you'll have between the 25th and the 30th to complete it whenever you have a 3-hour block. A good time to do it would be, just use this class time or whatever. Yep, so smart pointers. Okay, so I want to talk about these. These deserve their own, 10 or 20 minutes to talk about. But the basic idea is you can have a type, like something called a unique pointer, that only points to one thing. You can't have multiple pointers pointing to it. It's unique. Okay, so that avoids things like freeing your memory twice. We looked at some things with the copy constructors where we said, hey, if two things, if a shallow copy happens and two things are pointing to the same memory, that causes problems. So we can avoid a lot of those problems using our language. Okay. Let me get to the stuff you'll actually be doing though. Code coverage. So here's the little write-up from the wiki about what it is, but it's just measuring. It's a measure of how much of the code that actually executes do you have a test for. Okay. So what does that mean here? Okay, here's a practical example. I have some main function. This is also from the wiki of the tool we're going to be used, which is called GCov, the GNU code coverage tool. And I have some loop here, and it's just exercising different parts of this loop, based on the value I. Okay, so it's checking, do I actually execute this line here? Well, if I'm iterating I from 1 to 10, and I try to mod it by 11 and you get 0, one of these lines isn't going to get executed here. So then it gives us a report. It says, okay, after we run this program here, only 88.89% of the program actually runs. Okay, so you might want to look and say, well, what about the off chance that this happens to execute, or the user changes, I to 11 here? You would want to know about that, but there's no sort of coverage for that. Okay. So this tool, it's available on all the Linux machines, but I'm going to have folks SSH into Cori and run this because it's definitely there. It's an easy and quick tool to run our example on. And every operating system has a similar tool as well. All right, so here's just another example with things sort of covered here. And this is going to look a little bit more familiar to what I'm going to get to in the next 2 or 3 slides here, where we'll actually be writing our tests in a framework where we just have some sort of test here. And then we have some bool flag equals true, say if not flag. So if not true, so this is false, so this block of code is never going to execute. Sometimes your IDEs or text editors, a lot of people like Visual Studio Code, that you might be able to find different extensions or plugins that can do nice color coding and say, hey, this bit is never going to execute here. And it might actually visually show you. Okay. All right. So what is the testing framework that we're going to use? So assignment 4. You'll actually be setting this up, but I want to give you a little bit of a preview and just run this tool for you once so you see it before the homework. Well, there's really 2. We're going to focus on the first one. That's called Catch2. And it's a unit testing framework. It works. It was designed for modern C++. There's a nice talk about it if you want to see some more tutorial than what I'm going to give over the next between today and then the write-up in assignment 4. The other famous or popular one is Google Test. Google Test is a little bit harder to set up, so I want to minimize our sort of dependencies and how big our CMake files get. Both are commercially used. Both are used in production. Catch2 is the second most popular. Google Test, I think, is the most popular. But those are 2 sort of choices in C++. Actually, there's many choices. These are the 2 most popular. So Catch2, again, relatively simple to set up. It's one C++ file and one header file. Okay. If you look at the website, you can learn a little bit more about it here. But let me show folks an example here. I think I've got this code set up here from their help. So, let's see here. Biggest font. There we go. With this here. So we don't need to run it yet. Okay, so this is what Catch2 looks like here. At the very start, you're going to define this variable here. It's called catch config main. And actually, if I look through this file, there's no main function, okay, in this file. Okay, so all our programs need to start from a main function. Basically, if I define this symbol here, when I run it through the Catch framework, it's going to do a little bit of magic and create a main function for us somewhere. We don't care where, really. Because what we're doing is just building unit tests. Okay? Okay, so how do I use Catch2? Well, I include the Catch2 library here. I made things a little bit simple here, so it's called catch underscore, I can't pronounce this word properly, ameliorated. Maybe I'm butchering that, but all the files, all the functions that we need in the Catch2 framework are here. Okay, and then for this example, I'm just giving us a sample function that we can play with. Now, for us, we might do other stuff. In assignment 4, we're going to have to include app HPP, include our favorite command HPP, etc. Right, to give us access to all of our code. Okay, for now here we just have a test function. Okay, this is computing the factorial. Okay. All right, and then how do we actually use catch? Well, we start off with, well, let's just say macro. So usually when you see things all uppercase, that's a Catch2 macro. So test underscore case. I give it a name that factorials are computed, and then some other. This is like the section here, factorials. Okay. And then for this test case, I'm just going to require factorial of 1 is 1, factorial of 2 is 2, etc. Okay, and then maybe a big one here, my edge case. Okay, so that's it. And if I want another test case, I just copy this and add it here. Okay, let's just work with one here. And let's go ahead and run this. Let's see what happens. Make this a little bit bigger. Oh. All right. Here's how I build it. Make it in one line for you here. So it is a C++ 14 or above, so we're going to use 17. Here's the example file. That's what's up here. And we do need the Catch2 framework C++ code. So we've got one other C++ file that's being compiled as well. Okay, so let's go ahead and compile this. Let's give it a moment. Now it's going to take a little while to compile here because I'm compiling all this framework. That's okay. There are ways to speed it up, but this is the simplest way to just get us up and running. All right, and then we'll actually run this program that I compiled. And then, wow, that was fast. Okay. All the tests passed here. Okay. We had 4 assertions in one test case. Okay, that makes sense here. And scroll down. One test case, 4 assertions. Okay. Let me run it again. Oh. Well, it's running pretty fast. Okay, so that's it. We've passed all of our unit tests. This is how we're going to want to do our testing. Okay. So as a little preview here, let me show you assignment 4 here. We're getting to our wrap up here. So how are things going to change? All right, assignment 4. I've got my little to do. We won't look at that before this goes live. So here's the example, some comments, what your tasks are going to be, and just some examples of things you might want to think about. So this is how you'll actually be able to use your actual app that you create here. And here's app, HTTP, command, draw, etc. You could write your own little functions if you want. then you'll have a test case for, making sure you can initialize and destroy the app. Okay, so that would be an example test case. Then you have to think about, are these good tests and some other things here. Now the cool part is, though, that I'm going to show you is CMake, because I said CMake's going to be worth the pain eventually for those of us who are wrestling with it. But the cool idea here is in my CMake file, I actually have 2 builds going on with it at any given time. So I have one build that's our sort of normal build building our paint program. And the second build, I've got a test executable here. And that one's essentially going to be building all of our tests. Okay? So now I don't have to worry about if I have a debug, release version, or whatever. I just get both of my build files here for app test and app. Okay? So that way you'll be able to just run app test or app every time you build. Okay, so you'll actually see in your build file when you run make or whatever tool you're using, you get an executable for app, and then you get your app test one. Okay, and then if you want to run all of your unit tests first, you can do that. The point that we're eventually going to get to once you form your groups to is every time you push your code, since you'll have this app test framework, it'll run for you, and you can't push until you pass all of your tests. That's where we're sort of going. That's what we want to do that in a production setting. Okay, that's the right thing to do. All right, so that's where we're heading for testing. I just want to show you the Catch2 framework, because this is where we get into the kind of cool stuff in software engineering, building better software. All right, so there's some other cool things you can do with the Catch2 framework, which make it a good framework. You can sort of do this behavioral-driven testing, they call it. Let me make this a little bit bigger just so you can get the idea how to do this. Scroll down here. So here's an example where you actually describe scenarios that you want to happen. So this is getting into not just our teeny tiny unit tests, but actually a series of things that we might want to do. This is likely going to make sense for us because, right, we're painting pictures. So maybe we want to see if it's okay if we can paint 10 pixels and then undo and then do another paint. We might want to do a series of things, right? So we might have some sort of scenario called paints the Starry Night by Van Gogh, some sort of interesting thing. Given some factor, and then we have our sort of assertions while this is happening. So this is sort of a behavior-driven test. This is where we're going to move eventually, and what the framework allows us to do. Okay, so I think that's enough Catch2. We'll see it again when we have assignment 4, and then when we're working in groups as well. All right, so today we learned a little bit about software verification, validation, and some of the different tools in C++, how to do some of these different things, then about unit testing, a little bit at the end about behavioral-driven testing, what code review was, saw a little video, and so on. And review on test-driven development, which I think most folks have seen already. All right, so that's what I've got for the lecture. Your labs have been pushed. Show you what we're doing there. And then we'll break out into lab mode here. It's a little smaller. CPP testing. So a couple parts to today's lab. The first is doing the code coverage tool, so you can see which tests are executing. I would ask that you do this on Cori. You might have to clone your repository on Cori to get this and sort of run and play around a little bit with the copying and pasting, but you'll run it on Cori. Task 2, you'll learn how to write an exception in C++ and inherit from the exception class. So you have a few examples there. And then I want you to be thinking about, and you can collaborate with some folks about this, but how you'll do some less trivial testing for our painting application. What kind of tests will you write? What would be good functionality to test for our painting program? right? Where we can't just unit test everything. And that's what I got for you folks. Any questions before we break out? All right.
The assignment 4 gonna release today?
Not today. It'll be released after assignment 3, just so folks are focused on that one. But in 3 or so days. Yeah. Yep. So you'll have that out, and that'll be due a little bit after the exam, so you can just focus on the exam next week, and then assignment 4 after. All right, for folks who want to hang around and work on the lab, you're welcome to. Otherwise, I'll see folks in 2 weeks. I won't see you next week. We'll all be remote. So enjoy that.